Wasabi, guys. Welcome to Integration Bee Training for Advanced. This is part 9.2, and we're going to be still dealing with infinite functions, but we're going to be dealing with infinite functions in terms of Taylor series. Okay, so let's go ahead and get started with that. So there are infinite functions where we come across something like this. Now, you notice that, okay, we have an infinite function, but there is no reoccurring, well, there's a pattern, right? But there's no like reoccurring infinite functions where the inside is equal to the outside, right? In this case, you know, this infinite function is not that case. So how do we deal with this? Well, we use Taylor series, right? And you probably already know immediately that this is a geometric series. So because by geometric series here, this integral, we can actually use Taylor series because this is from 0 to 1. So because of that, this whole integral is equal to 1 over 1 minus x squared. Oh wait, but then we know this integral. This is easy. We know this integral. This is just inverse sine. It's arc sine. So this answer, this whole integral, is equal to pi over 2. Okay. Again, I know infinite functions. You're just not. It looks weird. It looks illegal, but it is mathematically true. Again, we can compute things like this, right? And of course, Taylor series. If you have an infinite sum, whenever you have an infinite sum like this, it's gonna become a Taylor series for some reason. N equals to 1 or 2, whatever. For some function, use Taylor series. Okay. We have this integral here. All right, we have an infinite something here at the bottom. So how do we solve this? So what we're gonna do, I'm calling this in blue, is we're gonna multiply this by 1 plus x squared. Top and bottom, 1 plus x squared. You're probably thinking, wait, why not just do 1 minus x4? You know, why? Well, it's because it's infinite, so we don't know where it's gonna, you know, turn out to, right? However, if we go like this, there is something, right? If we do 1 plus x squared, what does this equal? This is equal to 1 plus x squared plus x cubed, okay? And if you multiply 1 plus x to the power of 4, then this is going to continue off to x4, x plus 5, x plus 6. Let's see, this is 8. I'm sorry, 7. Okay. And then if we continue more, and it's going to be like this. And then whatever, it's going to continue when you continue infinitely. Okay? So, in other words, that whole denominator, when we multiply top and bottom by 1 plus x and 1 plus x squared, you just created a geometric series. Right? So that's cool. I know it's a little hard to see, but that's literally what we're doing. We're creating a geometric series in the denominator. Okay? Let me hold you off for a second. Let me hold you for a second. 10, 1 plus x. So we have this. And at the bottom, what do we have? We have 1 plus x squared, x cubed, x4, x5, dot dot dot. Okay. Can we actually use geometric series? Can we actually? What's wrong with our bounds? That's from 0 to 2023, right? So, can we actually use it or no? The answer is yes and no. And the reason is because from 0 to 1, oh, now you can use geometric series. It satisfies the geometric series. So because of that, we have 10, 1 plus x squared, and this denominator, is equal to 1, 1 minus x. Okay? Alright, nice. But what about the rest? What about 1 to 2023? Well, because this is infinite, and all these x's, they're like more than 1 or above 1, you know, it's going to get larger and larger and larger instead. And so now because of that, this whole bottom is like hella infinite. And so because of that, 1 over infinity, that whole thing is equal to 0. That whole thing is equal to 0. So what we actually have, our integral is from 0 to 1. We have 10, and we have 1 minus x to the power of 4 dx. Cool. So now we have x minus x5 over 5 from 0 to 1. 1 minus 1/5, that's 4/5. It seems that our answer is equal to 8. Okay? So again, watch out for the bounds, right? And then, again, from 1 to 2023, whatever is infinite, it's going to equal to infinity. Thankfully, because this was at the denominator, we technically had 1 over infinity, so the whole integral is equal to 0 rather than infinity, which is amazing. So, this integral converges, and it equals to 8. Alrighty, here's another integral I made. I believe this was for I think this is also for UC Berkeley Integration B as well. But you can already see where this is going to, right? Now you're probably thinking, oh, wait, this is an infinite function. Oh, I know how to do this, right? You know, you might do this, and then, you know, you're like, wait a minute, but then this is to the power of x equal to e of x minus 1, and then, wait a minute, this is equal to ln both sides. You get x minus 1, ln both sides. This is 1 over x minus 1, and then this is e to the 1 over x minus 1. Oh, well, okay. That's one way of doing it. Okay, cool. So, in that case, what we have is this integral is equal, let's see, this is ln. This is all happening inside ln. So we actually have this as our integral. Okay? And so now our answer is equal to ln of 2021. Alright? Another way we can solve it. What's another way of solving it? Another way of solving it is using Taylor series. Right? This whole inside, that inside here. This whole inside, this very whole inside here. Okay? This, we have e to the 1 over x, and then times, well, plus technically, e to the 1 over x inside of 1 over x, so this is technically 1 over x squared, and then 1 over x cubed, and then 1 over x4, and then dot dot dot, right? And so with that, this whole integral that we're dealing with is technically this, which does simplify to, well, we can use geometric series on this because, of course, you know, in geometric series, well, this is technically negative 1 x over 1. Negative 1 x and then 1. Between negative 1 and 1. So this, we need this to satisfy geometric series, right? However, in 1 over x, we can definitely use geometric series because in 1 over x, we have between 2 and 2022 as our bounds. Can we use geometric series? Well, let's see. Let's flip it. And when we flip it, oh, absolutely. Yes, because it is definitely in between -1 and 1. So here, we can absolutely use geometric series with the bounds from 2 to 2022. So, and of course with geometric series, we get 1 over x over 1 minus 1 over x, which also equals to 1 of x minus 1 dx. Okay, which is what we have before. This integral is equal to the ln of 2021. I'm sorry, 2021. Okay, that's our answer. All right, very nice. You can use Taylor series, or you can use the infinite function, the algebraic way that we did before. Okay. Whoa, now this looks very intimidating, right? It's kind of like, it's like reoccurring and there's a pattern at the same time. So it's like the algebraic method and the Taylor series method at the same time, right? But no, this is just Taylor series, right? So again, whenever you see something like this, okay, don't panic. Let's break it up. Let's simplify. Let's deconstruct this technically. Okay, so 2x over 2 technically, and then we have times 4 to the power of x, and then we have square root and square root, so it's over 4. Okay, times 8, x to the power of square root, and square root, so that's 8 here. Okay, I see where this is going. All right. But then we can actually simplify this a lot further, right? This is from 2 x half plus 4 is equal to 2 to the power of 2. So I'm not going to simplify it. I'm going to leave it like this, and you'll see why. 8 is equal to 2 cubed, so that's 3x over 8. 16 is equal to 2 to the power of 4. 4x over 16. Ah. There is a sum. There is a sum at the exponent. That sum, that we have here, equals to 1. We have 2 to the power of n with n. Okay. Of course, you can add x, but you can literally factor out the x. But you can have x in, but honestly, you can just factor out the x. So, okay. But what is this, right? What is this sum? How do we solve this sum? So, the way we solve this sum is, well, let's see. S is equal to a half, 2/4, 3/8, and 4/16, right? Now, because that denominator, there's a factor of 2, so if I do 2s, then I get 1, and I get 2 over 2, okay? Don't worry about this. I'm just helping you visualize what's going on, right? What's going on? Wait a minute, the denominators are shifted, right? So now let me lay it out like this. If I want to do 2s minus 1, this is 2s minus, and then s is here. And let me lay it out like this. Oh, what do you notice? It's shifted. It is shifted. So 2s minus s, when we subtract it, we get 1/2, we have 1/4, and we have 1/8. Oh, this is a geometric series. This is equal to 2. So our answer, this sum is equal to 2. Okay? So now that we figure that out, our answer, our integral, is 2 to the power of 2x dx. So our answer, 4x to the 4x over ln of 4 plus c. Okay, that's our answer. All right. Whenever you find, like, sometimes when we deal with weird, awkward-looking sums like this, you can just lay it out, let it equal to s, and then kind of shift the denominator in a way where you can kind of add or subtract two sums together and try to form a more well-known sum. Okay? In this case, we use the geometric series to solve this. Another way of solving this sum is this is also equal. I'm sorry, I'm going to write an arrow. This is also n 1/2 n. So if we know that the geometric series of 1/2 of n is equal to 1 minus half. Oh, I'm sorry. Let me write it like this. Okay? Where x is equal to 1/2, right? Then we know that xn is equal to x over 1 minus x, right? If we derive it, and the reason why I'm using x is because if I put in 1/2, you're going to think, oh wait, why are you deriving a constant, right? So that's why I'm using x, just so that you can understand a lot better. Deriving it, we get x n minus 1, but that minus 1, I can apply it to x here, and then I derived it, the derivative of 1 minus x. Okay? In this case, that sum is equal, let's see, this is what, 1 minus x squared. Let's see, x, we get 1 minus x minus x negative 1. So we get, so that cancels out, so we get 1 over 1 minus x squared. So this sum is equal to x over 1 minus x squared. And of course, in this case, what we have is x equals to 1/2. 1/2, that's also 1/4. This also equals to 2, which is exactly what we have. Okay? So you could do the derivative way. If it's easier for you, if calculus is a lot easier for you to see, you can do the derivative way. If algebra is easier for you, you can do the algebraic way, let this awkward sum equal to s, and then lay it all out, whatever, and then manipulate the denominator, and then add or subtract in a way that makes a familiar sum to you. Okay? Alright, so we have this infinite function here, where we have a square root, and then a cube root, and then a fourth root, and a fifth root, and it keeps on going forever. So, just like before, whenever we deal with something like this, try to just kind of deconstruct this infinite function, right? So let's go ahead, rewrite this as a square root. So we have 1/2, and then we have times x here. This is inside a cube root and a square root. So we have 1/2, and then times 1/3, right? Because there's a cube root inside of a square. I guess to make it easier for you guys to see, it's being cube rooted and inside of a square root. So the exponents multiply. They don't add, they multiply. So be very careful with that. Okay? And then times another x. And it's the same thing. It's 1/4 inside of a cube root, inside of a square root. And then here we have 1/5 inside of a 1/4 root, inside of a cube root, inside of a square root. And this product keeps on going forever, infinitely. Now, if we put it in exponent form, it's easy to see that this is a half plus, well, it's 3 times 2. There's 4 times 3 times 2, and 5 times 4 times 3 times 2. So it's going by factorial. So this is 3 factorial plus 4 factorial plus 5 factorial. I'm sorry, 1 over 3 factorial plus 1 over 4 factorial plus 1 over 5 factorial. And it keeps on going. Okay, so we do have a Taylor series for this. It is the sum as n goes from 0 to infinity, and we have where we have x to the power of n over n factorial. This is equal to e to the x. Okay, so this Taylor series is what we're going to be using, right? This is equal to e to the x. So what that means is what we have is if we only have 1 over n factorial, that's x equals to 1. So this means that this sum here is just equal to e. Okay, now you do have to be careful. This is n equals to 0. What we have, here, let me deconstruct this. So this sum, if you plug in 0, you get 1. Plug in 1, you get another 1. Plug in 2, you get 2 factorial. And then to 1 over 3 factorial, and then so on. Okay, so we only have this portion, but we don't have the 1 plus 1. So what we need to do is we need to add 2 and then minus 2. So what this is equal to is e, right, and then minus 2, right, because e needs the whole 1 plus 1. So what we're doing is we're adding 2 and then minus 2. And adding 2 gives us e, and then we have the leftover minus 2 here, dx. And this is just power rule. So by power rule, this is equal to x to the power of e minus 1 over e minus 1 plus c. Apply the same thing. This is a very similar infinite function, right? So you apply the same thing pretty much. So let's go ahead. We'll turn this into exponential form. Right, this is 1/2 plus, and then we have 2 over 3 factorial, and we have 3 over 4 factorial, we have 4 over 5 factorial, and so on. We already know where this is going. This is that exponent. If we just only focus on that exponent here, this is the sum as n equals to 1. And then this is, or actually, let's make this a little easier for us. Let's put at n equal to 2, and then this is just n minus 1, n factorial, right? So now, what we have here is this is equal, n equal to 2. This is like n minus 1 factorial minus 1 over n factorial. We can shift this to n equals to 1. So that's going to be n factorial minus n plus 1. Right? And so with telescoping series, this is just equal to 1. So what we have here, this whole integral, is just x. So our answer is just x squared over 2 plus c. Okay? Very fast. Again, just get comfortable with the summations. That's pretty much it. Just getting comfortable with summations. But we're getting there. Okay? This is our last integral. Now, I think a lot of people knows or have seen the integral where it's like the square root of x to the power of log, and that's like something like that, and it keeps going. It's like that integral, the infinite function, the infinite integral from black pen, red pen. Before I made that integral, the original integral was actually this, and I just kind of derived it, just kind of modified this in logarithm form, and that's how I submitted it to Berkeley Math Tournament. But we'll go ahead and start with this original infinite function that I had. So how do we deal with this infinite function? So again, like always, we just kind of deconstruct it and turn it into exponent form. So let's go ahead and do that. So we have e to the 2x. Here we have x squared over 2. Here we have x cubed over, well, it's inside of a cubed root and a square root. So this is 3 factorial. Then we have x to the power of 4, 4 factorial, and so on. We already know where this is. We see the pattern here, right? So, of course, like I've showed, we have a Taylor series from n equals to 0 to infinity. When we have x to the power of n over n factorial, this is equal to e to the x. So let's go ahead and deconstruct this Taylor series. We have, this is equal to 1 plus x squared over 2 factorial, and then plus x cubed over 3 factorial. Is that what we have here? Close, but not quite, right? So we do have an x, but we don't have a 1, right? So let's go ahead and simplify this. So we have e to the x, an extra e to the x here. And then the rest we have e to the x. However, we need that 1. So we add a plus 1, which is inside this e to the x, and then minus 1. Okay? And so now, what we have, this is just basic u substitution, right? This is 1 over e, and then this is just e to the u du, where u is equal to e to the x, right? And so now this is the answer is just e to the x minus 1 plus c. So our answer is e to the x minus 1 plus c. Okay? And that is it. So that's it for the Taylor series side of infinite functions. Again, you just have to kind of do this again, and once you start using a lot of these Taylor series, you'll definitely remember these Taylor series. So yeah, that's pretty much it. That's just kind of practice, rewatch the video, and try the integrals yourself. Alright, so I hope this helps. Thank you guys so much for watching, and I'll see you guys in the next part.